Hello and welcome. Today let's talk about a subject that everybody loves in math. That would be fractions. But I want to connect it immediately to some algebra concepts. I think sometimes there's too long of a delay between the time of learning fractions and then using fractions in algebra. So get some lined notebook paper and let's get started. All right, so the very first thing we need to start is what's the definition of a fraction? And this is key, and it's crucial to understand why we do certain things. Most students, when I say, hey, give me a definition of fraction, they'll come up with something very, very close. They'll call it, it's a part of a whole. And that's true, but you're missing a key idea. The parts have to be equally sized. So it is an equal part of a whole. So let's talk about just the way a basic fraction is written. We're going to use a horizontal fraction bar and use two lines of paper exclusively. We need to very clearly see the top and the bottom. Those have different names, and the most important part of the fraction is the denominator. The denominator is the bottom number on the fraction, and that tells us the most important thing about the fraction. That would be the number of equal parts that make the whole. Okay, so the denominator tells you how many equal parts then make up a whole value or one thing. Okay, the numerator then tells you, which is the top part, how many equal parts you have. Like I'm not comfortable with exactly how to phrase this. I sometimes will say how many equal parts you have, and then I had a student one time say, well, where do you have them, Mr. Marsh? I said, well, I'm in my pocket. Like I don't know. So how many equal parts you're talking about, how many equal parts there are, how many equal parts you're considering, something like that. So numerator and denominator, how many equal parts make up the whole is the most important thing, and then how many equal parts you have then is the top part. Let's have a little fun. I'm going to switch over to my document camera, if I can pull that up here. There we go. And I've actually got some little toys, if you want to call them that I used to use back in the day. They're little plastic pieces, and they're cut into equal parts to illustrate fraction concepts. And I used to use this back in the day with overhead projectors. That's how long I've had this. But let me scoot over here now and do some work with this. And I got some sun shining in my window, so it's like really, really bright. That's great. All right, so this is your whole. This is 1 out of 1. But if I take that, and you'll see that it's the same size as this next piece here, right? Are you convinced then that they are the same size, right? So if I take that same size piece and I break it into 2 equal parts, then this shows me halves. If I take the same size and I break it into 3 equal parts, then I've got thirds, and then this is broken up into fifths, okay? So if I took this part right here, right now what I've got is I've got 2 parts out of 2 total. So I've got a whole thing. But if I somehow were to like remove one, now I don't have 2 halves. Now this is just then 1/2. And if I pull one of these parts away here, now I've only got 2 parts out of 3. And if I pull 2 of these away, now what have I got down here on the right? I've got 3 parts out of 5. Okay, so the parts have to be all equally sized. And let me switch back over now to the standard screen. Okay, this is why now there's a problem if we try to put a 0 in the denominator, because a fraction is somewhat of a division question, right? It's something that's been broken, it's been divided into equal number of parts. Why is this a problem? Why is it a problem to say 3 divided by 0? Well, let's talk about what it means. The denominator here, 0, means the number of equal parts that make the whole. So how many parts make the whole in this one? 0 parts make the whole. But the numerator is how many parts you have. How is it how is it possible? How does it make any sense to have no parts make up the whole, but yet you have 3 of them? Like what? Like that doesn't make any sense at all. That's absurd. Okay, so division by 0, a 0 in the denominator of a fraction is not allowed. But this is allowed. You could have 0 on the top and a 3 in the bottom. Okay, 0 parts that I have out of 3 parts total. I could go back to my little fraction pieces and just take all of the orange ones away. Like how many do I have now? 0. That's fine. 0 out of 3 is 0. So that's allowed, but your denominator can't be 0 because it tells you the number of equal parts that make up the whole. If you don't have any equal parts of the whole, you've got nothing to begin with. So it doesn't make any sense. Okay, now let's talk about reducing of fractions. Let's say that I had a fraction that was 6/8. And you may say now, well, that can be reduced. And you kind of have an instinct with it in terms of numbers, but let's talk analytically about what's really going on. What I'm going to do is I'm going to factor a 2 out of the 6, which leaves me a 3. And then I will factor a 2 out of the 8, which leaves me a 4. And what's happening really is only things that are multiplied can be canceled by division. So if I factor a 2 out of the top and a 2 out of the bottom, now these factors can be considered their own little fraction. What is 2 divided by 2? Well, that's 1. So these are canceling. It's giving me 1 times 3/4. And what I have left then are my numerator and denominator that remains, 3/4. Okay, so 6/8 reduces now into 3/4. What does that look like now on the little pieces? Hang on just a second. Let me switch back over now to my dry erase board, and let me get rid of these, and let's erase those. And what was I doing? I was doing 6/8. Let me pull up my pieces of 8s here. Where have I got them? Here's my 8s. 1, 2, 3, 4, 5, 6. Oh, I can't pull it off the desk. I'm going to have to slide it off. It's kind of like stuck. There we go. Okay. Now, I've got 6/8. Didn't we say there was a 2 involved? Didn't we say 2 times 3 and then 2 times a 4? What's the 2 got to do with the little fraction pieces here? Well, if I take 2 of these and 2 of these and 2 of these, I've got little groups of 2. But now if you'll notice, 1/4 is exactly equal to 2 equal parts of 8s. And if you'll notice, if I lay that like right on top there, you can see that they are in fact, the same size. So I'm replacing 2 8s with 1/4 there, and 2 8s with 1/4 here, and 2 8s with 1/4. Where's my other one? There it is. With 1/4 here. So it's the same size. It's the same value then. 3/4. Okay, pretty nifty, huh? All right, so moving back now to what does it look like when we do something with an algebra extension to it? So let's do something like 54x cubed over 45x. Now analytically, I'm going to want to factor first. Now you may think, well, I already know kind of by instinct how that's going to cancel 54 and 45, but I want you to get in the habit of factoring first, because you'll have to do that when you do polynomials and things of that nature. Okay, so factor first. Let's factor everything. So 54, that's going to be 9 times 6, and then x cubed is already factored. It's got a single base there, right? And then an exponent. And then divided by what's 45 factored, that would be 9 and then 5 here, and then this would be just a single x, and maybe we could even write that to the first. Now, if I've got 9 divided by 9, the common factor then cancels, so this cancels out, and so what I'm left with numerically is going to be 6 on the top and the 5 on the bottom. Don't try to change that into a mixed number. Leave it as an improper fraction. Now, let's talk about the x's. What does cube mean? Cube means repeatedly multiplied. So that really means I've got 1, 2, 3 x's on top. And so just like the 9s, one of these will cancel with one of these, leaving me 2 remaining. So x squared on the top. If you want to think about it, it's just the 3 minus the 1. Because remember, a variable is a number. So just like the 9s would cancel, what if x was 7s? I would have, 7 times 7 times 7 on top and then a 7 on the bottom. And so one of the 7s will cancel with, on top would cancel with one of the 7s on the bottom. So it's just a number. So we treat it just like it would be a number. All right? So now let's discuss one more thing before we move on to another operation. Fractions are oftentimes confused with, because they're very similar to a ratio. Ratio is not exactly the same thing as a fraction, although it looks like it if you write it as a fraction. What's a ratio? A ratio is a comparison between two values. And so it's not exactly a fraction. On a fraction, the denominator told you how many was the whole, and the numerator told you how many parts that you had. But it doesn't have to be that way with a ratio. Let's say you're a sportsy kind of a person, and you want to discuss your win to loss ratio for your team. And so let's say that your team has won 8 games, and they have lost 6 games. That's a pretty good win-to-loss ratio. You're over half, right? You've won more than half of your games. But 6 isn't the total number of games. 6 is only another part. The total then would be 14. But still, you might talk to one of your friends, and your friend says, well, my team only won 4 of their games. And you might think in your mind, I've got a better team than they, because our team's won more games. But wait a second, without knowing how many the other team lost, you really can't say. And if they've only lost 3 games, then just like with a fraction, oh my goodness, those relationships are the same. The ratio of 8 to 6 is equal to the ratio of 4 to 3, because we're not focusing on the numbers themselves, we're focusing on the relationship between them. And this is crucial then. It's a step upwards in understanding of numbers. Not just the numbers individually, but the numbers in relation to other numbers. And so if you've been in my classroom, you've seen my 7 liberal arts posters. I had this poster made. I put this together. I did not invent the 7 liberal arts. Those have been around for 3,000 years or so. But I put the poster together because it's important. The first 3 are the language arts, but the last 4 are the mathematical arts. The first one's arithmetic, and that's just absolute quantity. That's the property of the number itself as an individual thing. So you can do odd, even, prime, composite. You can even do basic operations and things like that, getting a number, add, subtract, multiply, divide, and so forth. But the next thing after that is surprising to most people. It's music. Music is the second mathematical art. And music, we're defining it as relative quantity. You thinking music is a mathematical art? Yes, because what you're doing is you're discussing quantities, numbers if you want to call them that, not absolutely by themselves, but numbers in relationship to each other. And a key concept in music is this idea of harmony, which is not one note, it's 2 notes, either sounded at the same time or maybe sounded at different times, like it's a melody or something like that. You ever notice that sometimes 2 notes, when you play them together, they sound really, really good? Oh, I like that. And then other times 2 notes that you play together, like that's kind of dull, that's not really interesting. And then other times notes that are sounded together are bad, like they make you cringe. That's like that's tension. I don't like that, right? The issue is not the note. The issue is how the note responds in relationship to another note. It's the relationship among those things, and that is a musical concept. And it's more than just sound. Our common understanding of music is just sound. But this goes back to the ancient Greek mythology of the muses. It was all the things that you perceive with your senses and the things that please the senses. So it's the right relationship among space, or right relationship among color, or right relationship among all sorts of different things. So the category of music there really should be modernly defined as fine arts. It would include painting, sculpture, architecture, dance, you name it. So it's looking at the relationship among those things. And so I thought that was an important point to make here when we're talking about fractions and ratios. But anyway, moving on. Now let's talk about the thing that really gives folks problems: adding and subtracting fractions. When you add or subtract fractions, you must have a common denominator. I would bet $1 that most of you knew that, maybe all of you. But why? Why do you have to get a common denominator? Let's explore why. Let me take 1/2 and let me say I'm going to add it to, what have I got? I'll add it to 1/3. Okay? And let me switch over to the little fraction pieces, and we'll have this discussion here, and we'll talk about why we have to do that. So let me clear this out. Let's see here. I need 1/2. There's my 1/2, and then I need 1/3. So I'm going to write it down like this. I'm going to say 1/2 has to be added to 1/3, and it's going to be equal to something. Okay? Now, how do I add things together? If you remember what addition is, it's combining two or more groups into one total. So I'm going to take these two pieces, these are two parts, and I'm going to put them together. I'm going to go, oh, look, there we go. So here, I got something over here. What have I got? How many pieces do I have? Because that's what the numerator says, like how many parts we've got. Oh, I've got 2 parts. How did you get that? Well, I took 1 plus 1. That gave me 2 pieces. Hey! But what's the denominator? Well, some students want to take 2 plus 3 and say 5. That's totally wrong. That's like embarrassingly bad. But it's like we added the top ones together. Why don't we add the bottom ones together? 2/5? Really? I've got 2/5? No. This piece is a 1/5. This piece also is another 1/5. Is that equal to what I've got right there? Not even close. Okay? But wait a minute. Why are the pieces sized that way? Why is that green piece that's a 1/5 smaller than a 1/3? Because the definition of a fraction is that they're equally sized pieces. So what we have to do before we add them is we have to get the pieces to be equally sized. And that is what you're doing when you're getting a common denominator, right? The denominator tells you the size of the pieces because they're all equally sized. And if you cut it into more pieces, they're going to be smaller. You cut it into less pieces, they're going to be bigger. So before we can even add these pieces together, we've got to get a common size. So let's just play with this one here. If I were to get a common denominator, that would be, if you can follow the math, maybe not. I'm going to move that camera down a little bit. Still not showing all of it. There we go. Let me straighten it out a little bit. Sorry about that. Common denominator would be 6. Now, how do I change these individual fractions? Notice I'm just doing one full denominator, 6. How do I change these fractions? Well, what do I multiply 2 by to get 6? I'm going to multiply that by 3. And if I multiply the denominator by 3, I have to multiply the numerator by 3 because I'm really multiplying by 1. 3 over 3 is 1. So what's 3 times 1 there on that one? That becomes 3. So my 1/2 right here now has been changed into 3/6. It's the same value, but it's in a different form. But it's still equal to the same thing. This one, if you remember, you would have to say, well, we're going to multiply that by 2. And so this one times 2. So this new numerator becomes 2, and then my operator goes right in the middle there. So I get 3 plus 2. I do the operation now on the numerator only. Notice how I've set that up. 3 plus 2 would be 5, and the denominator, 6, not 2/5. Okay? Now, let's go back and let me talk about why we do it that way. 1/2, I'm actually going to break that into 3 more equal pieces, which will give me 1, 2, 3, which will give me 3/6. Hopefully you can see now if I put those on top of each other that they are exactly the same size. So there's my 3/6, which is equal to 1/2. So now we're done with that. And then a 1/3, I'm going to break that into 2 more equally sized pieces. And the way the numbers work out is now these pieces are all equally sized. So break that into 2 pieces. Doing a replacement now. I've got 3/6 plus 2/6. What have I got all together in the end? I've got 5/6. Okay. Now, how would you do that algebraically, though? Well, okay. We did it with numbers. Let's do it now with some algebra. How about 5 over 4x? That's supposed to be a 4. Plus 7x over 10. What's the common denominator between 4x and 10? It doesn't matter that x is a number that you don't know. Just do the numbers that you do know. What's the common denominator between 4 and 10? Hopefully you see that 20 is the numerical value. But I need to include this extra little thing right here, right? If x had been 3, I would just had to have multiplied 20 by 3, right? So let's just go ahead and leave it in as an x. Okay? Now I've got to adjust my existing denominators. How do I adjust? How do I multiply 4x so that it gives me 20x? 4x times what is 20x? That would be a 5. So the first fraction needs a 5 multiplier in the denominator, which means I'm going to have to do a 5 multiplier in the numerator because I'm really multiplying by 5 over 5, which is 1. So this new numerator becomes 25. Notice I'm just using a single denominator. All right. Now, the right-hand side, what do I multiply 10 by to get 20x? That would have to be 2x. And so if I do 2x on the denominator, I have to do 2x in the numerator, and it's the whole numerator times that. So what's 7x and 2x? That's going to be 14x squared. And what goes in the middle? My operator right there. Operations only go in the numerator. Okay. Now, can I add 25x plus 14x squared? No, they're not like terms. Can I reduce anything at all? Don't be tricked. I can't, but somebody might want to try. Somebody might want to say, oh, the 25 and the 20, those can be reduced, and that would give me a 4 right there, and that would give me a 5 right there. But you can't do that because you have to divide everything by 20, and 14x isn't divisible by 5, right? This is illegal canceling. Let me show you a simpler example of illegal canceling. If I said 4 plus 1 all over 2, here is illegal canceling. Divide the 2 and the 4 out. That's going to be a 1 and that's going to be a 2. So my final answer, 3. But that's crazy. The numerator, 4 plus 1, is a group. That's 4 plus 1, that's 5 over 2. 5 over 2 is not in any way 3. Okay? Division does not cancel things that are added or subtracted. Look here. It's 4 plus 1. Division does not cancel things that are added or subtracted. It only cancels things that are multiplied. So like if you remember back when we reduced the first thing, I had to factor everything. Okay? Now there is a way that you can maybe partially reduce it. If I come back in here, let me clean this up a little bit. I could say this is 4 divided by 2 plus 1 divided by 2. I got to take the 4 over the 2, and I also have to take the 1 over the 2. I got to do both of them. 4 over 2, you could say that that's 2. So 2 plus a half, yeah, that's 5 halves now. That would work. Okay, but in this algebraic expression here that we've got, I can't reduce anything. Okay, it's best just to leave it just like that. Could maybe break it into 2 parts over 20x, but like there's no advantage to that. So I'll just leave it as 25 plus 14x squared all over 20x. That's as far as I can go. All right, now adding and subtracting sometimes involves groups. So let me give you another example to work with. 2x plus 7 all over 6 minus 5x plus 1 all over 9, okay? Get a common denominator there for that one. That common denominator is going to be 18, okay? So a single fraction bar, single denominator. Now, put parentheses around all of your numerators and denominators because they are groups. And this wasn't as important earlier as it is right now because that 2x plus 7 on the left and that 5x plus 1 on the right, that is an entire group that now must be adjusted. So what do I multiply 6 by to get 18? That's going to be multiplied now by 3. But if I multiply the denominator by 3, I have to multiply the whole numerator now by 3. And so let me just drop that package right down in there. 3 times the group of 2x plus 7. Notice I didn't even multiply it in. I just took that whole package that had been adjusted and dropped it down as my first numerator, okay? The negative sign right here now drops in. But now on this side, I have to multiply this by 2. And I have to multiply that by 2. And maybe I'll bring the 2 out in front here because that's the way it's normally written. It's minus 2 times the group of 5x plus 1. Okay? So notice all of my operation is up in the numerator. I just have a single denominator. If I wanted to simplify this now, I would then multiply the 3 in and multiply the negative 2 in and collect my like terms, and maybe it would reduce or something like that. But the key idea here that I want to share with you is that when you multiply the numerator or the denominator, if it's got like more than one term, you have to do it as a group. Okay, that was the main point there. All right, now let's go back to some easy stuff. In order to multiply fractions, in 4th grade or so, you probably were taught, oh, just multiply straight across, and that's true. 3/4 times 8/7, you would just multiply straight across. You don't have to get a common denominator. So that then would be 28. And then you can reduce, factor out the 2, factor out the 4. 4 times 6 there, and then 4 times 7 there, and now the 4s will cancel, leaving me 6/7. But notice we had to multiply it really big first, and then we had to reduce it down. If you had a savvy 4th or 5th grade teacher, they might have taught you this. 3/4 times 8/7. Let's reduce before we multiply, because any factor on top can cancel with any factor on the bottom, right? This is still just 3/4 times 8/7, and maybe I can think about it all just as a single fraction. This 8 right here will cancel with the 4 right here, leaving me a 1 and a 2. And the 3 and the 7 don't cancel. But what I have left now when I come across is the 3 times the 2, 6, divided by a 1 times a 7, 7. And there we go. You might think, boy, that's a little shortcut, but I like my other method better. You can't do that when you do algebra. When you're doing big polynomials and then you're multiplying them all together, you don't want to multiply them and make them even bigger still and then try to reduce them because you can't reduce them. They're too large. So you have to factor everything first and then cancel common factors before you multiply and then multiply afterwards. Now let's talk about 2 things that are a bit of a problem that I've seen recently. One is multiplying a whole number by a fraction, 5 times 3/4. I've seen students do this. They will take the 5 times the 3 and call it 15, and then for some crazy wrong reason, they do the 5 times the 4 also, and they call that 20. What? No. What's the denominator there? 1. Okay, 5 times the 3, 15. That's cool. 1 times 4, 4. Okay? Do not multiply both the top and the bottom by the numerator. No. And maybe the problem is that they write it as they mess up the structure. They will say 5 times, and they'll write this as a fraction like that. Instead of using 2 lines, they use a single line and they squeeze it up in there. Now maybe it does look like the 5 goes with the 3 and the 5 goes with the 4 because it's kind of in the middle of them. But really what's happening here is that you are misplacing the fraction bar. I see a fraction bar in the 3/4, but where's the fraction bar on the 5? Right there. Do you see how the fraction bars are misaligned? It really should be not 3/4 on a single line. It should be 3/4 on the two lines, and now you see the 5 only aligning itself with the 3, not the 4 at all. Okay, so be mindful of that. But multiplying a fraction by an integer is actually oftentimes beneficial, as we'll see in a minute. What if I had something like 3/4 and it was multiplied by a number that canceled the 4 entirely, like 8? Okay, I can multiply that through and call it 24/4, but let's look at this. Wouldn't it cancel if this is 8/1? And you can always write in over 1 if you want to do it that way, if you want to make sure that you have the denominator in the right spot. Doesn't this 8 and this 4 cancel? It does. It leaves me with a 1 here, and this cancels and leaves me with a 2 here. So 2 times 3, very simple now, 6. Notice there's no fraction. There's no denominator. Well, there is a denominator, it's 1, but we have an integer that remains, okay? This is going to be important in a moment. All right, almost finished. Next, let's talk about proportions. Proportions are a unique arrangement. They are two fractions that are equal to each other. And we kind of saw this a little earlier when we were reducing fractions and so forth, or we were comparing those two win-loss ratios. But let's talk about two fractions equal to each other. Let's use the basic one, 3/4. And if I said now that that's equal to something, something, something here over 8, what number must go in the numerator to make it equal in its relationship to 3/4? Hopefully you understand by instinct maybe that that would be 6, but let's talk about analytically why. One of the properties of proportions is that the cross products are equal. If I multiply diagonally through, what's 4 times 6? 24. Hey, what if I multiply 3 by 8 through? Also 24. So what I could say is this. I could say 4 times 6 must be equal to 3 times 8. Okay, you agree with that? Good. Now what happens if I have an unknown? Let's say, what if it was 3/4 is equal to x over 8? Here's what I would do, is I would solve this by setting the cross products equal. I would take the 4 times the x, and I would write it as 4x, and then I would take make it equal to 3 times the 8. But I wouldn't even multiply it out. I would just leave it like that. Because the very next step I'm going to do is divide both sides by 4, divide both sides by 4, and this all cancels, and I usually, hopefully, will get some reduction here. The 8 and the 4 will cancel, 2 and a 1. And so x then equal to 6, 3 times the 2, just like we had said previously. Yeah? So proportions are fairly interesting. They're simple equations, really, but oftentimes I think they get overlooked, and so students will come across a proportion then and there. They think it's something strange and unusual and maybe hard, when it's not. It's really rather simple. You solve proportions by setting the cross products equal. And maybe you saw this a little bit in some algebra that we've done previously, where you had something like y minus 3 over x plus 7 is equal to, I don't know, 3/4, right? When we're doing equations of lines, and then you have to treat those as a group, and then you can set the cross products. These two multiplied, so 3 times x plus 7, and that's got to be equal to these two multiplied, 4 times y minus 3, and notice now we're just dealing with integers, okay? So proportions. All right, last part, and this is maybe the best part. Equations. When you're working with equations that involve fractions, you can do something special. Previous to all of this, up until proportions, we were dealing with not equations, we were dealing with expressions. And the property of expression is that you have to maintain value. The values have to stay the same. That's why we had to adjust those fractions by getting a common denominator by multiplying top and bottom by the same thing, right? We're multiplying by 1. We didn't change the value, although we changed the structure of the numbers, but the value of the overall thing stayed the same. But with an equation, you can change the values, provided that the values stay equal. So for equations, to solve equations, we're going to multiply everything by the least common denominator, and that will eliminate all of the denominators. So for example, if I had, let's say here, 3x over 4, I don't know, plus 5 is equal to, let's say, 1/2. Okay? I could get a common denominator of everything and do the math, but I don't have to because of this equal sign right here. Because you remember the rule of equations is whatever you do to one side of the equation, you must do to the entire other side, or y dot c whatever I'm toss. Okay, what I'm going to do is I'm going to multiply everything by the least common denominator, and the denominator on the 5 is 1. You can write that in there or not. You probably could are too savvy enough to really bother with that now. But anyway, so what's the least common denominator between 4 and 2? That would be 4. So if I multiply the entire left-hand side by 4 and the entire right-hand side by 4, notice my parentheses around both sides. Here's how it plays out, and this is great. Okay, if I distribute the 4 into this group, it becomes 4. Well, let me just skip a line here so it's not quite so cluttered, because you need to see what happens. This is glorious. 4 times 3x over 4, and then it's plus 4 times the 5, and then it's equal to 4 times 1/2, okay? And now watch what happens with these denominators. Starting on the left, the 4 here cancels entirely with that 4 there. All I have left is 3x. Nifty, huh? Plus, what's 4 times 5? 20. Equals, now the fraction on the right. This entire denominator cancels out, but leaves me a 2. So I take the 2 times the 1 that's there, 2. And now look at that equation. 3x plus 20 is equal to 2? That's fantastic. Doesn't this become 3x is equal to negative 18? If I subtract 20 from both sides? Then divide by 3 again, divide by 3 again. Oh man, look at that. X is equal to negative 6. Nice. Does that make my denominator 0 anywhere? That's always important to go back and check. No, it doesn't. Okay, good. See, that was so much better than doing it with the fractions. Okay, so you're going to multiply everything through by the least common denominator. I meant to do that. Good. Fractions. Don't let it scare you. But you got to master your fraction skills and understand what you're doing before you get into algebra. Because if you can't do fractions on numbers that you do know, how in the world are you going to do fractions on numbers that you don't know? You can't kind of like do a shortcut and use a calculator. Anyway, may your day be merry and bright, and may all your mathematics be right.